Hi, in this lecture, we are going to prove the Cook-Levin theorem. Remember, the statement of the Cook-Levin theorem is that if 3 sat is in P, then P is equal to NP. Let us see the proof. Okay, so given M, W, and C, we wish to compute a formula, a 3CNF phi, such that the phi is satisfiable if and only if there exists a y of length polynomial in the input length, so length at most length of w to the power c, such that M accepts wy in time at most length of w to the power c. This is just the definition of NP. The computation, the construction of phi will take polynomial time. And this is going to prove the theorem, because if 3 sat is in P, then we can decide satisfiability of phi in polynomial time. Okay, it is slightly convenient to let k denote length of w to the power c, so that we make the expression a little bit simpler. So if you do that, you just have a k here. And now we're going to open up this definition using our definition of accept. Remember that the machine accepts the input w, comma y, if there exists a sequence of configurations where C1 is the start configuration, which is Q0 per wy, and Ck is the accept configuration, and for every I, Ci yields Ci plus 1. The variables of phi are the symbols in Y. Okay? And C1, C2, .ck will be encoded in binary or true false. So for example, we can encode a state with the bits 001, a open bracket with the bits 010, and so on. Okay, the first claim that we make is that the length of each configuration is at most k. And why is that? That's because the Turing machine runs in time k, so it uses at most k tape cells. This is one aspect of the proof, which is made easier by our working with Turing machines, because a Java program could go fetch items from the memory which are very far, and it is harder to come up with a short description of the configurations. Okay? Recall that and for all are just all the same, have all the same meaning as just the and that's used in SAT. Okay, so when I say and here and I put for all, it's just a big and. Okay, so I can put an and here, an and there, and make a big and here over I that ranges from 1 to k. Okay, so now it starts ready to look like a 3CNF. The important difference, the important thing that's missing is the yield notion. So recall that the end over I of Ci yields Ci plus 1 means that C1 yields C2 and C2 yields C3, and then Ck minus 1 yields Ck. Now we need to rewrite yield in a way that looks like a formula. And what do you think we're going to use of Turing machine computation? We're going to use the locality of Turing machine computation to rewrite yield. So the yield becomes this. Okay? It becomes another and for j at most k, that the 6 symbols here, the j, j plus 1, j plus 2 symbols of ci and ci plus 1 are consistent with the Turing machine transition function. Okay, so as we mentioned earlier, the variables of phi are the symbols in y, and also the configuration, the C1, CK. What is the formula phi itself? What do you think is phi? Phi is this. This whole thing here would be your formula phi. As you can see, you just have exist here, and the formula phi is expressing this. So it's a bunch of ends, and these consistency checks just concerns 6 symbols, so it can be written as a Trissian F. And the equality with this, or the equality with an accept configuration, also can be written as a Trissian F. So with a little bit of patience, it's not hard to put this into the Trisat formula. And this concludes our proof overview. So we have finished the proof of this cornerstone result in complexity theory, the so-called Cook-Levin theorem. Bye now.